Hi, in this video we are going to talk about AVL trees focusing on the height parameter of a given binary tree. So, let's get started. Okay, you may pose the question that what does it mean the height of a node or a vertex? It is basically the length of the longest path from this given node to a leaf node. So we can use recursive formula to calculate the height of a given node. The height is going to be equal to the height of the left child and the height of the right child. Basically, we have to calculate the maximum out of these two values and we have to increment it by 1. So for example, we have this tree-like structure. The root node is the 20, we have the 10, 40, 30 and 50. The leaf nodes have the height parameter 0. And it's very, very important that the leaf node basically doesn't have any left child or right child. In this case, we assign a height parameter -1 for these null references. So for example, the vertex 10 doesn't have any left child or right child, but in this algorithm, we suppose that there's a left child with height parameter -1 and there's a right child with height parameter -1. Why is it good? Because this is how we are able to calculate the height parameters for the leaf nodes. Unless we would get a null pointer, we are not able to calculate the height parameter with this recursive formula. Okay. So the AVL algorithm uses height of the nodes, so we want the height as small as possible. Why is it good? Because if the height parameter is as small as possible for all the vertices, it means that the binary tree is going to be balanced. If the binary tree is going to be balanced, it means that the logarithmic running time is going to be preserved and it's going to be very fast. It's very important that we have to store the height parameters. If it gets high, we have to fix it with the help of rotations. Okay, and we come to the conclusion that all subtrees' height parameter couldn't differ more than 1. If it's true, then we know for certain that the tree-like structure is balanced. If the left subtree and the right subtree height parameter differ more than 1, it means that this tree is unbalanced, so we have to fix it. So for example, we have the vertex 40. It has a left child, 30, and a right child, 50. Both of them have a height parameters 0. So, we have to decide what's greater, 0 or 0. It's going to be 0, and we have to increment it by 1, and it's going to be the height parameter for the parent. So that's why the vertex 40 is going to have the height parameter 1. What about the root node? The root node has a left subtree. Okay, it contains a single node, the vertex 10, whatever. It has a height parameter 0. What about the right subtree? The right subtree contains 3 vertices, and basically the height of the subtree is going to be equal to the height parameter of the root node of this subtree. So that's why the right subtree of the root node, which contains 40, 30 and 50, it's going to have the height parameter 1, because the root node of this subtree, which is the 40, has a height parameter 1. So we have to calculate the maximum out of 0 and 1, it's going to be 1, and we have to increment it by 1 in order to get the height parameter for the root node, and that's why it's going to be 2. Okay, so AVL tree requires the height of left and right child of every node to differ at most +1 or -1. Here we come to the conclusion that the difference between the height parameters are exactly 1. It's not going to be greater than 1, and that's why we can come to the conclusion that this tree is balanced. We don't have to rotate it. Okay, so basically we have to check whether the absolute value of the height of the left subtree minus the height of the right subtree is going to be smaller or equal to 1 or not. If it's smaller or equal than 1, it means that the binary tree is balanced. If it's greater than 1, it means that we have to rotate it, we have to make it balanced again. So we can maintain this property in ordo log n time, which is quite fast. The overall logarithmic time complexity is not going to be violated. So what about the insertion? It is a simple binary search tree insertion according to the keys, but then we have to fix the AVL property on each insertion. Okay, and what is this AVL property? Is basically that the height parameter couldn't differ more than 1. If we know that it is greater than 1, then we have to make the rotations. If it's smaller or equal than 1, we know that the tree is balanced. We don't have to bother about it. There may be several violations of AVL property from inserted node up to the root node, so we have to check them all. What does it mean? That maybe with rotating a subtree is going to make the parent subtree unbalanced. So maybe we have to make several rotations, but okay, we can do it in logarithmic time complexity, it doesn't matter. Okay, so we have been discussing the rotations. What does it mean? For example, we have root node D, it has a right child E, and it has a left subtree with the B, the A, and the C. We can come to the conclusion with the help of the height parameters that the tree is unbalanced. Then we have to make these rotations. And basically it's very important that we just have to update the references, which can be done in order 1, so constant time complexity. So, for example, if we would want to make a right rotation on the D, so the root node, then basically the left child of the root node is going to be the new root node, the D is going to be the right child of the B, and it's very important that the C is going to change in the sense that it's going to be the left child of D after the rotations instead of the right child of B. So I think it's pretty intuitive. We just have to rotate the whole structure to the right. What if we want to rotate to the left? For example, we start with the right subtree with the root B, the left child A, the right subtree with the root node D, then C and E, and we just have to rotate it left. So the D will be the root node again, the B will be the left child of D, and so on. So you may come to the conclusion that yeah, if we make a right rotation and a left rotation, then we end up the situation where we have started. And it's very important that the in-order traversal is going to be the same. What's the in-order traversal for the left subtree? It's going to be A, B, C, D, E. What's going to be the in-order traversal in the right subtree? It's going to be A, B, C, D, and E. So that's why these rotations are very handy. We can make sure that after the rotations, the tree-like structure is going to be balanced, so the running time is going to be okay, and it's not going to change any property of the tree. For example, the in-order traversal, when we store characters in nodes, then it's going to yield the alphabetical ordering. When we store numbers in the nodes, then it's going to yield the numerical ordering. Okay, so this is how we make rotations. We can rotate it to the right and we can rotate to the left. And it's very important that we have to check on every insertion whether the height parameters are okay or not. If the height parameters are not okay, then we have to make these rotations. We can do it in order 1 time complexity, but maybe we have to make several rotations. And that's why rebalancing a tree is going to take logarithmic time complexity in the main. And it's very important that the in-order traversal and all the properties of the tree is not going to change. So for example, the minimum item, of course, is going to remain the minimum. The maximum item will remain the minimum. Thanks for watching.